calibration of the device. So in front of you we've got the structure of the device. We've got galvanometer, standard resistance, variable resistance, and cell. And the two terminals, the post-test terminal and the negative test terminal, the positive test terminal and the negative test terminal. Okay, the device is short-circuited. Positive test terminal is connected to, yes, -1. Okay, and the pointer should give full scale deflection for the current, which is 0 deflection for the resistance. We call this, we zero the device. Zero here is a verb. Okay. A resistance, external resistance, known resistance of 1 ohm is then, yes, inserted between the two test terminals. So what do you expect the pointer of the galvanometer to do? Yes, it moves backwards. Total resistance increases, the current decreases. So the pointer moves a little bit backwards to a position, to a new position where the value of the known resistance is written. Okay, we placed 1 ohm resistor, we know its value. Okay, pointer retreats, moves backwards, so we write the value of the resistance, which is 1 ohm. Okay, we'll do the same with another resistance, let it be of 2 ohms, and we'll write the value of it till we build up the scale of the ohm meter. Okay, so we managed to build up a new scale for the ohm meter for ohms. Okay, why we say a new scale? Simply because we've got one scale, first scale, but for current. And now how to measure an unknown resistance. The unknown resistance, denoted by R, is inserted between the test terminals, and the pointer directly reads its value. Let me say it again. The unknown resistance, R, is inserted between the test terminal and the pointer directly reads its value. The current flowing through the device is determined from the expression VB over RG, RS, RV, RG plus RS plus RV plus R internal plus the unknown resistance denoted by capital R. And now we've got give reason. The ohm meter scale is reversed to the microammeter scale. The scale of the ohm meter is reversed to that of the galvanometer. Galvanometer, we call it microammeter device or microammeter scale. Let me say it again. The ohm meter scale is reversed to the microammeter scale. Because the current intensity flowing in the device is inversely proportional to the total resistance. So when the resistance increases, the current decreases. Another give reason. The ohm meter scale is not an evenly divided scale. Let me say it again. The ohm meter scale is not an evenly divided scale. It's not uniform. Why? This is very important question. Because the current flowing in the device is inversely proportional to the total resistance. The current is inversely proportional to the total resistance. What does it mean, total resistance? It's not inversely proportional to the measured resistance alone. If it was inversely proportional to the measured resistance, the scale would be uniform, but it is inversely proportional to the total resistance. And now let's solve some problems. A milliammeter of resistance, millimeter means a galvanometer, of resistance 5 ohm, reads full scale deflection for a current of 15 milliampere. So Rg is given to be equal to 5, and full scale deflection of the milliammeter, it is Ig, and it is 15 milliampere, so it is 15 times 10 power negative 3 ampere. It is desired to convert it into an ohmmeter using a cell of 1.5 volt of internal resistance 1 ohm. We want to convert, yes, the milliammeter into an ohmmeter, and we'll give you a cell of 1.5 volt. Internal resistance of the cell is 1 ohm. Calculate the external resistance, the value of the external resistance, which when connected to the ohmmeter, the pointer of the milliammeter reads 10 milliampere. Let's do it one by one. First of all, resistance of the galvanometer of the milliammeter is 5 ohm. Rg equals 5 ohm. Full scale deflection, which is Ig, I maximum, 15 times 10 power negative 3 ampere. Internal resistance of the cell 1 ohm. Vb equals 1.5. So Ig or I maximum equals Vb over Rg plus, between two brackets, Rs plus Rv. We call it R conversion, Rs plus Rv, resistance of the, yes, ohmmeter. So I maximum equals Vb over Rg plus R conversion plus R internal. So R conversion, as I said, is equal to Rs plus Rv. So maximum current given in the problem 15 milliampere. So 15 times 10 power negative 3 equals Vb, which is 1.5 over resistance of the device 5, internal resistance 1, and R conversion, the resistance which we need to convert the device into, yes, an ohmmeter. In this way we managed to obtain the value of the, yes, R conversion. It is 94 ohms. And now 10 times 10 power negative 3 is equal to 1.5 over 5 plus 1 plus 94 plus the value of the external resistance, which makes the pointer of the milliammeter, yes, stands at 10 milliampere. So 10 times 10 power negative 3 is equal to 1.5 over 5 plus 1 plus 94 plus R. So it's all easy to calculate the value of R. It is 50 ohms. Another type of question, what happens when? What happens when? Okay, the current in each wire is doubled. In front of you we've got two wires, wire A and wire B. And the currents flowing through the two wires, yes, are in the same direction. And we want to know what would happen if the value of the current in each wire is doubled. The distance is made 4 times greater, is quadrupled. Okay? Concerning the force acting on the two wires. While the direction of the current in wire A only is reversed. Okay? So let me remind you, with the changes here. Current through each wire is doubled. Distance is made 4 times greater. Current in just one wire is reversed. Okay. We want to know what is the result on the magnitude and kind of the force per unit length acting on each wire. Okay. Since the formula that determines the magnitude of the force, size of the force, is given from the expression 2 times 10 to the power of negative 7 I1 I2 L over D. So we can say F is equal to 2 times 10 power negative 7 I squared. Why I squared? They carry the same current intensity. Okay, so I squared L over D. The formula is modified into F1 over F2 is equal to I1 over I2, yes, squared, times D2 over D1. Given in the statement of the question, I2 is equal to, yes, 2I1. Distance is made 4 times greater, so D2 equals 4D1. Substituting, so F1 over F2 is equal to I1 over I2, which is equal to I1. I1 will be crossed out and squaring, do never forget. D2 equals 4D1 over D1, so the result will be 1. It means the size of the force, the magnitude of the force will not change. The magnitude of the force remains unchanged, but the force becomes repulsive one. Kind of the force it changes. Instead of being attraction force, it will be repulsion or repulsive force. What would happen if the shunt in an ammeter is replaced with another of lower resistance? Shunt of an ammeter is replaced with another of lower resistance. Okay, with respect to the sensitivity of the ammeter and the maximum current that the ammeter can read or that the ammeter can measure. Okay, thank you very much. Yes, right. Sensitivity of the ammeter decreases. Sensitivity of the ammeter decreases, it means the device, yes, is enabled to measure higher current intensity. And the ammeter, as I said, can read greater currents. In front of you, we've got a circuit which contains a cell, a battery, which is connected to R1, variable resistance, R2, and we've got 2 voltmeters, V1, okay, across the cell, across the battery, and it measures external or terminal voltage. V2 measures the voltage across R2. And what about the question? The switch in the circuit is closed with respect to the readings on the voltmeter. It means the switch was open. When it was open, yes, V1 was reading V battery. It was maximum. V1 was maximum. It was equal to V battery. But when it was open, V2, yes, was equal to 0. V2 equal to the current times R2. Current, no current flows as the circuit is broken, okay? So V2 was 0, V1 was equal to VB. When closing, what would happen? Thank you very much. V1 decreases, but V2 increases. V1, instead of being V battery, it will be just an external voltage. V2 was 0, but now it has got a value, so it will increase. Okay? So V1, as I said, decreases, but V2 increases. The value of R1 is increased. Another type of question. Now we've got a circuit and the switch is closed, but we changed the chosen value of the rheostat. we increased the value of R1. Okay, with respect to the readings on the 2 voltmeters. Okay. What about your answer? Of course, thank you very much. When increasing R1, total resistance of the circuit increases. Okay, the current passing through the circuit, when the total resistance increases, the current decreases. Okay, and internal voltage, which is the product of current and small resistance, or small, depends on the current. So internal decreases, and of course V external should be increased, because some of them is the V battery. So once again, when R1 increases, total resistance increases, current decreases, internal voltage decreases, but V1, which is the external voltage, increases. And V2 depends on the current, so current decreases, V2 decreases. So once again, V1 increases, but V2 decreases. Let me say it again. When R1 increases, R total increases, and current decreases, internal voltage decreases, so external voltage, which is V1, increases. V2 is obtained by the product of I, R2. R2 is constant, so it depends on the current, which was decreased, so it decreases. Once again, increasing the value of the variable resistance increases the total resistance of the circuit, so the current through the battery decreases, which results in a decrease in the internal voltage, so terminal voltage, which is V1, increases. V2 decreases as it is proportional to the current. Yes, another circuit. What would happen when the switch, or when the key K2 in the opposite circuit in the circuit shown is closed? When it is closed, we are disconnecting R1. R1 is disconnected from the circuit, as if it is removed from the circuit, so total resistance decreases. Okay. And of course, it asks with respect to the reading on the voltmeter and that on the ammeter. Okay. V decreases, but reading of the meter increases. Why? As I said, when closing the switch, R1 is disconnected, is removed, so total resistance of the circuit is decreased, current flowing the circuit is increased, V internal is increased, V external is decreased. So V is decreased. Current, as I said, is increased, so reading of the meter increases. Once again, switching key 2 on disconnects R1, so the total resistance of the circuit is decreased, and the current through the battery increases, which results in an increase in the internal voltage, so terminal voltage decreases. When does each of the following quantities equal 0? Another type of questions. It asks, when does each of the following quantities equal 0? When does the torque acting on a coil carrying an electric current and placed in a uniform magnetic field equal 0? Okay. It happens in the vertical position. Torque equals 0 in the vertical position, where the plane of the coil is perpendicular to the magnetic field. Okay, since torque is given from the expression BIAN cosine theta, so torque equals 0 when theta equals 90. Cosine 90 equals 0. When does the magnetic flux at any point along the axis of a current carrying solenoid is equal to 0? When does it equal 0? Okay, thank you very much. When the solenoid is made of a doubly wound wire. when the solenoid is made of a doubly wound wire. In this case, the current flowing in one branch produces a magnetic field equal and opposite to the current flowing in the opposite branch, so they cancel out. When does the force of a magnetic field on a current carrying wire equal 0? Okay, thank you very much. It's all easy for you. When the wire is placed parallel to the field. When the wire is placed parallel to the field, the force of the magnetic field on the wire is then equal to 0. Why? Force is determined from the expression BIL sine theta. When it is placed parallel, theta equals 0, so the force equals 0. Okay, as I said, theta is equal to 0. Sine 0 equals 0, so the force is then equal to 0. When does the terminal voltage of a cell equal 0? Okay, this is very important. Terminal voltage is equal to 0 when the cell, yes, when the cell is short-circuited. What does it mean, short-circuited? When the two poles of the cell are connected without a resistance. When the cell is short-circuited, that is to say their terminals are connected together with a wire having no resistance. Okay, when does the difference between EMF of a cell and terminal voltage is 0? When does the difference between EMF of a cell and the terminal voltage equal 0? Okay, in other words, when does the EMF is equal to the terminal voltage, or when does the terminal voltage of a cell is equal to V battery? Okay, thank you very much. When the circuit of the cell is open, that's to say the resistance across the terminals of the cell is infinite, no current flows, then terminal voltage is equal to V battery and the difference is then equal to 0. Another possibility, when the internal resistance of the cell, yes, denoted by R small, is 0. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.